Again, I'm recording this because I've taught drawing Bohr and Lewis diagrams in many different ways, but this is a little different, and I notice we have quite a few people away, and I don't have a smart board like I did in the other room, so I can't actually do it smart board way. So I'm actually just pointing the camera at the board here, and I'm getting a shot of that. We're going to need periodic tables for this. Again, I suggest that you print out your own, but I know sometimes it's really hard to remember when you get home to print them out. It's not a big deal, but if you have one, that's great. If you don't have one, just raise your hands. I'm going to give you a copy of the ones that I use. So raise your hands in this row. You got one, Thomas? Nice. Excellent. So there's 3. How many in this row? 1, 2, 3, 4. Excellent. How many in this row? 1, 2, 3, 4. Not a problem. And 1, 2, 3.
I don't need one.
Oh, you don't need one. I'll take one back. Awesome. And here? 2 or just 1? Nice. Okay. And again, if you've printed your own, I know there's not many of them. When we get working away on this, if you see ideas, right, that you want to add to it to help you remember how to use the periodic table, by all means on your own table you can add that, like with a pencil. When we do a test, I'll be giving you something like this, which means you won't have all those nice little reminders, but when you're studying, you'd at least be able to look at those reminders and get those. Okay, so what we want to do today, all right, and I've got my camera pointed at the middle. That's really not going to be functional, is it? Anyway, I'll write it at the middle. I'm just looking at my own camera here and just going through it. So what I want to do today is I want to basically talk about how we represent atoms when we draw them. All right, these are not necessarily what we think that atoms look like. Remember, in the last couple of lessons, we've talked about atomic theories, right? Starting with Democritus, he used the word atomos. And then Dalton, he just imagined spheres. And then Thomson, he imagined the electrons in the spheres, like the Jell-O and the fruit salad, which only a couple of us knew what we were talking about. But anyway, and then Rutherford shot those little pieces at the atoms and discovered the nucleus, the positive center, and the electrons going around. And then the last day we talked about Bohr and how there's certain orbits, right, and how the electrons can jump up and down. So what we want to do now is, and actually there's one more complicated representation. I'll just show you for a minute. We definitely don't talk about that in this class, but this chart represents what we really think the orbits look like. And you'll notice not many of them are circles. Some of them are circles over here, but these guys, they look like, I don't know, they almost look like dumbbells, right? And over here they look like clovers. Right? So we now know that they're not actually simple circles. They're very complex structures. And I teach that to the grade 12 university course. All right? I teach that next level. But for you guys to understand chemistry, we don't need to worry about those crazy shapes. We're just going to think about how many electrons there are in the orbits. All right? So what we want to do today is we want to talk about representing atoms. Representing atoms, all right? How are we going to represent our atoms? Again, this is not what we really think of as being the atoms, but it does help us out. I am going out on a limb videotaping this and putting it online because my bad spelling is going to be shown to all of the world, but that's okay. Anybody who watches my videos know I've got bad spelling. All right, so in the past, in grade 9 and 10, your teachers might have given you a sheet or maybe had you draw all the Bohr diagrams for all the first 20 of them, all right? Now, in the end, that's what the sheet is that I'm going to give you. And then we always ask you to discover some trends. What do you notice about the number of orbits? And what do you notice about the number of electrons, right? This is probably where Kara's mind goes, oh my God, I don't even know it. Right? Yeah, okay. So what I want to do is I want to turn it upside down. I want to show you how to use the periodic table to get the picture, as opposed to drawing them and then having you discover all those trends. So we're going to do it differently. Hopefully it's easier, all right? Hopefully it makes more sense. A couple of things we need to remember. we are going to need to know the number of protons, all right? So the number of protons, and that for a neutral atom is equal to the number of electrons. So the protons and the electrons, we need to know those numbers. And that's the same as the atomic number, all right? So the number of protons and the number of electrons is equal to the atomic number. Easy to remember also when you focus on my voice. All right. So the atomic number on our tables is up here in the left. So you guys can see the atomic numbers on your chart as well. Okay? Hydrogen 1, helium 2, lithium 3, beryllium 4, etc., etc. So that's going to tell us the number of protons and neutrons. We need to define one other thing. Valence electrons. So this is a definition, and you can write it off to the side. I know I've got a table in the way, but that's okay. Does anybody know what valence electrons are? What are the valence electrons? This is a word we use. Anybody know? Not a problem. Valence electrons simply means the outer electrons. So they're the electrons in the outer shell, the outmost shell. The term valence, and you don't have to know this, but the term valence comes from the same word as valor, right? So if you're in a group and you have a lot of valor, it has to do with power, all right? It also is the same root word as Valhalla, which I think is where dead Norse people go. You know what I mean? The dead Vikings go to Valhalla. That's their idea of heaven or something like that. It means power. Where did this word come from? In chemistry, it came originally from the idea of having the power to bond with something. Before chemists knew anything about electrons, they did know that compounds contained more than one element. And so then you would have had something like H2O. Don't write this down. H2O. So oxygen had the power to bond with two H's. And you would have something like NH3. Nitrogen had the power to bond with three hydrogens. And CH4. Carbon had the power to bond with four hydrogens. And so we now know this power to bond comes from the electrons themselves. So we still call them valence electrons, all right? It just means the outermost electrons. And the reason we're only interested in the outer electrons is because they're the only ones that are involved in forming chemical bonds. They can be shared, they can be traded, so only the outer electrons we're concerned about. Okay, so let's now deal with some Bohr diagrams. So off to the side, and I'm just looking to see how far I can write so that you can see me. Let's first do Bohr diagrams. Bohr diagrams. Bohr diagrams. Now in the past, we would have just did a bunch of examples, and then we would have had to do a whole bunch more, and then we would have discovered some stuff. But let's flip that upside down. Let me tell you what the Bohr diagrams will consist of. The Bohr diagrams, all right, they start with the number of protons in the nucleus. All right? So in the nucleus, we put a circle with the atomic number in it. Okay? Bohr diagrams also contain all the electrons. We're going to finish the lesson talking about Lewis diagrams, which only contain the outer electrons as dots, all right? Bohr diagrams are the ones that have all the electrons with all the rings, all right? The valence electrons, right? Or the outer, and I just want to define it again. The outer electrons equals the group number. Okay? The outer electrons is equal to the group number. So, group 1, group 2 We don't deal with the transition metals because their electrons are very complicated. This is group 13, but we don't involve the 10. So we pretend that the 10 is gone. Three electrons in the outer shell. 4 electrons in the outer shell. So this number up top, 1, 2, ignore the 10, 3, 4, 5, 6, 7, 8, tells us how many electrons we put in the outer shell. Okay? So that tells us how many to put in the outer shell. All right. So, valence electrons equals the group number. I'm just checking my notes to see what I want. The number of orbits is equal to the period number. All right? So the number of shells or orbits we put is the period number. Which means if I have hydrogen, it's in period 1. There's only 1 orbit. Lithium, all the way over to neon, 2 orbits. 3 orbits, 4 orbits, 5 orbits. Okay? The number of electrons, right, in the orbits, they follow a trend. How many electrons go in the first orbit? Does anybody remember? Yep. 2. We can get that from the periodic table. Take a look at the first period. How many elements are in that first period? 1, 2. So only 2 electrons go in the first period. The periodic table's shape is actually determined by those electrons. So 2 go into the first. How many electrons will go into the second? 8. 1, 2, 3, 4, 5, 6, 7, 8. So this tells me how many electrons go into each shell. How many will go into the third? 8. 8. And then we're going to stop at calcium. And that's because the transition metals have complex structures. The reason they have complex structures has to do with those ugly pictures that we're not going to teach you about in this course. So we're only going to stop at calcium, okay? So the electrons in the orbits go 2, 8, 8, and then we're going to stop at calcium because we don't want to get into the complex ones, okay? You might think if you count across it's 18, but it's not as simple as that, okay? All right. And just to finish, only up to calcium. All right? And the reason is the transition metals have complex structures. All right? And therefore, we're not going to deal with anything beyond calcium. All right? We'll just draw Bohr diagrams up to that. You might say, why do we even draw Bohr diagrams? Sometimes when we analyze things, and we're going to be doing some analysis later on, we need to take a look at that atom. We need to think about what happens when electrons leave or when electrons come. That's why we need the diagrams. All right? So we're not doing it just for fun. We're doing it because we're going to need these diagrams to analyze stuff later on. So let's do some examples. I'm going to put the examples just down here. I'm going to erase. So let's go with example. And you can just put these along in some spaces, however you want to put it on your paper. I'm going to erase again. I'm looking at my video. I can see it here. Let's start with a simple one. Hydrogen. All right? So let's use the rules that I've just written down. I'm not going to slide back and forth all the time, but we start with the number of protons in the nucleus. And remember, that comes from the atomic number. The atomic number. So, Kara, what's the atomic number of hydrogen? 1. 1 proton. plus 1. I know in grade 9 and 10 they might have made you subtract to figure out the number of neutrons. We don't care about the neutrons. The neutrons do not contribute to the chemistry. Sure, there could be neutrons in there, but we don't care. Okay? How many orbits will this have?
1.
Because it's in the first period. Now, in previous grades, don't draw this, but your teacher might have had you do a big old circle and put dots all over the place, right? Does that sound familiar? We are grade 12 college students. All I want to know is how many electrons are in that shell. I draw a semicircle with a space in it, and I put the number 1 right there. I'm not going to draw all those dots. I'm not interested in the dots. I'll draw the dots later on. What does this tell me? Hydrogen has 1 proton, and it has 1 electron in the valence shell, or outer shell. All right? Now I could go ahead and do helium, and we could go all the way along, but that defeats the purpose of me kind of teaching it backwards. Let's just pick another one. Let's pick carbon. So I'm going to erase here because I just want the room and I want to be able to talk like this. Does everybody have that information written down? We've got that. So let's now do carbon. All right? Again, in the nucleus, the atomic number in the nucleus. What do you got there, Doug?
6.
Plus 6. How many orbits will this have? Skylar? 2. I'm leaving the space to put the numbers in it. How many electrons go into the first orbit? Doug?
2.
2, because it's full, right? And it can only hold 2. Now, how many electrons will be in the outer orbit? Remember, that comes from the group number. So how many in the outer orbit? Ryan? 4. Now notice, the number of protons is equal to the total number of electrons. Awesome. Last time you would have done this, you would have did it differently. You would have said, I need 6 electrons, I need 2 to go in the first, and then there's 4 left, 4 in the second. But I want you to be able to use your periodic table to find the outer electrons. It's really all about the outer electrons when it comes to chemistry. And in the end, if you did it right, that should add up to that. All right? Let's do another one. Let's do neon. Can I erase? We're okay? Everybody's keeping up with me? Let's do neon. Now, the only way in which you can get better at something is to try it yourself and then see if you did it right. It's called building confidence. So, I suggest when we get to a point in a lesson and you think you know how to do it, you go ahead and give it a try. Don't wait for me. If you're unsure because you're using pen and you don't want to make a mess out of your nice notes, get a pencil. You can always erase the pencil. All right? Neon, right there. Atomic number, 10. Second period, group 18. Have you got a picture drawn, Dawson? Have you got a starting to a picture?
Yeah.
What do you got to start with?
10.
10 in the middle. Nice. It's a good start. How many orbits? How many orbits? 2. Blank. Blank. Do you have more information there, Dawson? Nope. How many electrons go in the first orbit? Yep. 2, because there's only 2 in the first row. That's how you can remember. How many are going to go in the second orbit? Yep. 8. It's in group 18. We ignore the 10. 8 in the outer shell. That means neon has a full outer shell, right? That's why it's a noble gas. It doesn't need to do anything to get a full outer shell. All right? Let's do one more. Calcium. Calcium. Again, give it a shot. Now I've got to pick on some people that don't raise their hands to make sure we understand what's happening. Zach, you are flying through. You're just charging on through, aren't you? That's exciting. All right, Kara, I'm going to pick on you. Well, because you say that you struggle to understand. It's my job to help you understand. It is fair. You'll get better marks. It'll be good for you. It is fair. Calcium. Can you find it on your periodic table? I love the disgusting, oh yes. All right, this will be the last time. If you get this straight up, I'll give you a break for a while.
Okay.
What am I putting in the middle?
20.
Plus 20. How many orbits?
4.
4. How many in the first?
I don't know.
Use your periodic table.
2.
2. How many in the second?
8.
8. How many in the third?
8.
8. Now, how many in the outer?
2.
2. Very good. That's correct. All right? Use the table. The table tells you. The table tells you all the answers. It's all on there, right? So that's why I wanted to flip it over. I didn't want it to be, total them all up, because that doesn't tell you anything. The table tells you how to draw it. Okay? Now at this point, I'm going to pause here.